everyone. Welcome to the course on digital signal processing. This is lecture 2, and in this lecture we will see what are the various techniques to design a IR filter. So, in our last lecture, we have seen various key points associated with the design of the IR digital filter. So, what are the techniques? What are the transformation techniques over here? So, first is approximation of derivatives. Second here is the impulse invariance transformation, and the third technique is called as a bilinear transformation. So, we'll be studying these techniques, and one by one we will see what are the advantages and what are the limitations associated with the design techniques of IR filters. So, we'll start with the impulse invariance transformation. It is basically, this technique is a bit obsolete. So, we are going to start with our impulse invariance transformation technique. So, what happened in this impulse invariance? In this particular technique, the desired impulse response of the digital filter means Hz, or we are talking about the impulse response, so we can say H of n is obtained by uniformly sampling the impulse response of the equivalent analog filter. So, HP, where A is for analog filter, so we are getting this impulse response of the digital filter by uniformly sampling the impulse response of the analog filter like this. This is the key point, that H of n equals to HA, and instead of T, I am using T equals to N capital T, where capital T is called as a sampling time or the sampling interval. So, the transformation technique we can well understood by first considering the simple distinct pole cases. Means if we have a simple poles like 1 by s plus 2, 1 by s minus 3, something like that. So, if we have the simple poles of the analog filter, which is of, let's say, this type, H of s equal to summation I equals to 1 to m A of I, AI s divided by s minus pi, where pi is the pole, ith pole. So, we are choosing the simple poles over here. The impulse response of the system can be obtained by utilizing the inverse Laplace transform. So, for this particular scenario, we will be having the property 1 by s minus a. The inverse Laplace transform will be e raised to power at u of t. Why u of t? Because we are considering that the filter is causal. If the filter is causal, definitely it will be right sided. So, that means we have ut over here. So, if we'll obtain the impulse response for this ai divided by s minus pi, so I'll be having ai e raised to power pi t and ut, where a is associated with the analog filter, and ut, it is a unit step function in a continuous domain. So, this is our third equation by applying the inverse Laplace transform. Now, this impulse response of the analog filter will be transformed to the impulse response of the digital filter with the help of the process called as uniform sampling. So, instead of t, I am going to put t equals to nt in this from our equation number 1. So, instead of t, I will be having h a n t equal to summation e raised to power pi n t u of n t. Now, since I am interested in calculating or finding the system function of my digital filter, so the impulse response, so the system function of the digital filter can be obtained by applying the Z transform to the equation number 4. So, we have the equation of Z transform h of z equal to summation n equal to 0 to infinite h of n z raised to power minus n. So, by utilizing this equation number 4 in this, I'll be having this summation h of z, and instead of hn, I'll be putting the same value over here. Now I'm going to change the order of summation. This summation I equal to 1 to m will go outside, and the summation n equal to 0 to infinite will go inside, like this. We're going to interchange this. And again, so we have summation n equal to 0 to infinite ai e raised to power pi nt and like this, u of nt. So because of this, it's an infinite GP, which is first term divided by 1 minus common ratio. Summation n equals to 0 to infinite r raised to power n 1 upon 1 minus r, where r is less than 1, like this. Then only the summation will be converged. If r is greater than 1, definitely the summation will be diverged. The result will be infinite. So hz equal to the simplified one, I'll be having summation I equal to 1 to m ai divided by 1 minus pit z inverse, where t is again the same thing, the sampling interval. Now we'll consider our equation number, we'll compare our equation number 6 with the transfer function of the analog filter, which is h of s. So if we'll compare, so 1 by s minus pi is corresponding to 1 divided by 1 minus e raised to power pit z inverse. So on the basis of this equation number 7, I'm going to find out that what is the relationship between the s domain and z domain. So if we'll compare, if we'll put s equal to pi, or if we'll put pi equal to s in this one, so I'll be having a relation which is z equal to e raised to power st, where this particular factor is called as mapping factor. Mapping factor means it will be mapped s domain to z domain, s domain to z domain. So the general characterization for the mapping z e raised to power st can be obtained by simply substituting s equal to sigma plus j ohm and by expressing s equals to z equals to I raised to power j omega. So we'll put I raised to power j omega to the left and e raised to power sigma t and e raised to power j ohm t, and I'm going to compare the real part with the real part to the left hand side, and the complex part will be compared this side. So r equals to e raised to power sigma t equation I'm getting on comparing the real part, and omega equal to ohm t. So that is the next equation which we are getting if we compare the imaginary part. So first, the equation number 2 basically gives a relationship between the two domains, means the digital domain frequencies and the analog domain frequency. And also the first equation r equals to e raised to power sigma t, it basically gives the location of poles, whether the analog domain poles are mapped in the z domain or at what location. So the location can be obtained by using this particular equation. So next is we need to analyze these two equations, this mapping factor we need to analyze. So if we'll consider our first equation, so the first equation is r equals to e raised to power sigma t. Now sigma less than 0, we can assume t any value. Let's say we can assume t equal to 1 second, and if we'll assume sigma less than 0, any negative quantity, so e raised to power some negative quantity, definitely it will be less than 1. And when sigma is greater than 0, so any quantity which is greater than 0, e raised to power some positive quantity, definitely the value must be greater than 1. And sigma equal to 0, if we'll put here, so I'll be getting r equals to 1. So sigma equal to 0, we are already aware that if we are moving on j omega axis from like this, then we are getting a circle in Z domain. Also, the left hand side, which is sigma less than 0, this region sigma less than 0, this is sigma greater than 0. So sigma less than 0 naturally will be mapped inside, and sigma greater than 0 definitely will be mapped outside. So this will give the location of poles of analog domain to the location of poles in digital domain. Now rest is the, so here this is on the basis of it is on the basis of this location of poles, the stability we can comment upon. So the stability of filter or the system is related to the location of poles. For a stable analog filter, the poles must lie in the left hand side of S plane. That means the stable digital filter poles should be lie inside the unit circle in Z plane. So this is the stability point. Now we'll consider our second equation, which is omega equals to ohm t. So if we'll put, let's say, ohm is between pi by t and minus pi by t. So the corresponding, I'll be having omega minus pi 2 plus pi. So if we'll be having, this is 0, this is pi, and this is minus pi. So it is actually plus, and this is actually minus pi by t, and greater than minus pi by t and naturally less than pi by t. So if we are moving in this particular region, what happened? What happened over here? Let's say we'll talk about this part only. We are moving on the geometric axis right now. So what happened here? That I'll be moving between minus pi to pi over here. Means the frequencies in the analog domain which are mapped between minus pi by t to plus pi by t will be mapped between minus pi to pi in Z domain, in the digital domain. Now what next? If ohm is pi by t and less than 3 pi by t, what we are getting? We are getting omega pi and 3 pi. Means pi to 3 pi. So this is pi, this is 2 pi, and again this is 3 pi. So again we are moving in the same, means again we are at the same point. It means we are moving again in a minus pi to pi region. Whereas in analog domain we are moving from pi by t to 3 pi by t. So that means we can say that similar point is for negative also. If we have ohm between minus pi by t to minus 3 pi by t, then again we are mapping, we are moving again in between minus pi to pi. That means here is very key point, that many frequencies which is ohm in the analog domain, which basically exists from minus infinite to plus infinite, they are going to be mapped in digital domain, in Z domain, between minus pi to pi. That means this type of mapping is called as many-to-one mapping. So many-to-one mapping, the stability of a filter is related to the location of poles, we are already aware, and the mapping is many-to-one. So this many-to-one mapping we can see in case of impulse invariance transformation. So many frequencies in the analog domain are mapped in the same region in the digital domain, which is between minus pi to pi. So that creates a aliasing. And aliasing is highly intolerable. Why it is aliasing? Because the frequencies in the digital domain are always the higher order frequency in the analog domain are again lying between minus pi to pi, means they are superimposing on each other, higher order frequencies. So that's why it creates aliasing, and aliasing is highly intolerable. So that's why we can say that this particular design technique is not suitable for designing a high pass filter or higher frequency filters. So this technique is used to design the low pass filter. So these are the key takeaway from this impulse invariance transformation technique. So the advantage is that first of all that the analog filter is stable. That means definitely the digital filter is going to be stable. But at the same time, if we are designing a high frequency filters, so definitely it will create a problem. It will create a aliasing effect in digital domain, and the filter will not be appropriately recovering the high frequencies as per the limitation. So this filter is used to design the low pass filters. Now here we have a summary. As per the mapping factor between the relationship between the analog domain frequency and the digital domain frequencies, whatever the frequencies are between pi by t to 3 pi by t, they are also mapped between minus pi to pi. And in general, we can say that 2k minus 1 pi by t less than, this omega is greater than 2k minus 1 pi by t and less than 2k plus 1 pi by t, where k is an integer, will also be mapped between the same minus pi by 2 minus pi to pi in the z domain. Thus, the mapping from the analog frequency ohm to the frequency variable omega in the digital domain is many to 1. This kind of mapping is many to 1, which simply reflects the aliasing due to the sampling of the impulse response. We are already aware in sampling when the aliasing occurs. Aliasing occurs when we are performing undersampling. If we are doing the undersampling, so definitely there is a aliasing effect. Now we have some useful cases over here, that if we have the multiple poles, if we have the multiple poles, so what is the corresponding S domain to Z domain transform? So you can learn these results also, these three results. This is first one, this is second one, and this is third one. So these results can be directly applied to transform an analog filter into a digital. Now, based on this, we have certain numericals over here that is associated with the infinite impulse response filter, whose transfer function Hs is given. Now, the basic theme regarding this is that how can we design the Hz? So the basic steps is we'll be having Hs. So first of all, I'll be calculating the impulse response of the analog filter, which is Ht. After that, instead of Ht, I'll be putting t equal to Nt, and I'll be having like this. And this is equivalent to H of n. And finally, by utilizing the Z transform, I can have the system function of the analog filter, digital filter, sorry. This is analog filter, and Hz is the system function for digital. So this is a whole basic process for the designing of IR filter using impulse invariance transformation technique. So how can we start with this? We can start something like this, that if we have H of S, if you remember the results, S plus A divided by S plus A whole square plus B square. The inverse Laplace transform of this type of Hs is e raised to the power minus at cos of bt, and since it is causal, so I can include ut also. So now Now we can have A equal to 0.2 by comparing with the generalized equation over here, A equal to 0.2 and B equal to 3. So since again it is in a standard form and the process is quite same, that will be calculating first h of t, and this ht can be converted into h of n by replacing t equal to nt. And fortunately what happened, capital T is 1 second in this. So h of nt is equal to h of n. And after that we'll be applying Z transform to calculate the system function of the digital filter. So this is the first type of problem where we have the second order equation in the denominator. Now we'll see one more complicated case over here where we have the analog transfer function, analog filter transfer function is given, and again we need to determine h of s using the impulse invariance transformation. Now there is a very key point over here is that since we don't have the sampling interval mentioned, so here we can assume capital T equal to 1 second. Capital T equals to 1 second. Now what are the steps? So the first step here is that we'll be having h of s. So from h of s I can first calculate, I need to just find out, step 1 is partial fraction. So once we have the partial fraction, so our analog system transfer function is basically converted into the most generalized cases, what we have already seen over here, that whenever we have a simple pole, when we have a complex poles, like that. So we'll be having, we can get those standard forms with the help of the partial fraction. Once the partial fraction is performed, we can calculate the ht by using inverse Laplace transform. So now once this ht is known, instead of t in ht, I will replace t equal to nt and capital T, where capital T we have already assumed equals to 1 second. So only the thing is, instead of t we need to replace h of n. So this h of n is the impulse response. It is the impulse response of digital filter. So now on the basis of this, again we can comment upon the stability of the filter by seeing the impulse response. We are already aware that the stability can also be checked if we are using that summation n equals to minus infinite to infinite mod of h of n, if it is absolutely summable. Then also we can conclude that the system is stable, absolutely summable. If it follows, so definitely the digital filter, whatever we are going to design, will be definitely stable. So this is the additional information which we can achieve with the help of impulse response of a digital filter. Now from Hn, I can calculate h of z using Z transform. And again also from Hz, the system function, we can calculate the location of poles and we can check whether the poles of Hz are lying inside the unit circle or outside the unit circle. So as per this particular numerical, we have the partial fraction. Now how to achieve the partial fraction? It can be represented as a by s plus 1 plus bs plus c divided by s square plus s plus 2. Again we'll cross multiplying this side and we'll compare the coefficient of the numerator over here with the constant 1. So the coefficient of s square will be equal to 0, the coefficient of S is also equal to 0, and the constant is equal to 1. So we have 3 equations, and right now we have 3 variables. So 3 equations can be easily solved, and we can achieve A, B and C. A equal to 0.5, B equal to minus 0.5, and fortunately we are getting C equal to 0. So we can represent now, this is H of S. Now again, this is not in a standard form. Since it is simple pole, we are already aware, we can directly write down what is the respective HZ, but this is not in a standard form. So to make this in a standard form, what we'll do is, we'll make this as a whole square. So S plus 0.5 whole square, by adding and subtracting in this one, and we can make this whole square. Now I just want to utilize S plus A divided by S plus A whole square plus B square. So S plus A 0.5. So I'll be adding 0.5 in the numerator. Also I'll be subtracting from the numerator, and S plus 0.5 divided by this minus 0.5 divided by this. So after this, you can take the inverse Laplace transform for all 3 cases individually, and you can replace t equal to nt in that, and by applying Z transform, we are getting the transfer function of a digital filter. So this is the overall transfer function, which looks bit complicated. So that's why the simple invariant transformation involves a lot of calculations. So this is the final result what we achieve. So if we'll calculate the location of poles for this particular filter, definitely the filter is going to be stable. So now in the next class, we'll see that what are the limitations, what are the limitations of impulse invariance, and we're going to start with our new transformation technique, which is called as bilinear transformation. These are the references. Thank you.